At 8:32 in the morning, on May 18th, 1980, a mountain in Washington state vanished from the map in less than 30 seconds. Not from the crater at the summit, but the entire north face collapsed completely, triggering the largest recorded landslide in human history. That landslide traveled at 240 kilometers per hour, carrying 2.8 cubic kilometers of debris, burying the Lateral River Valley under 60 meters of material. To picture the scale, imagine all of Manhattan buried under debris, nearly 7 stories deep. But that was only the first event in a chain of simultaneous disasters unfolding across a single morning. Today, we will walk through every second of that day to understand why this mountain permanently changed how we think about volcanoes. Before we discuss May 18th, we need to understand why this mountain exists here in the first place. Mount St. Helens is part of the Cascade Volcanic Arc, created by the Juan de Fuca tectonic plate subducting beneath the North American continent at 4 centimeters per year. As this oceanic plate descends deeper, it carries water and minerals that lower the melting point of surrounding rock, generating magma that rises beneath the mountains above. St. Helens was called the most dangerous volcano in North America by American geologists because of its continuous eruption history spanning 4,000 years. In 1980, the surrounding area was paradise for campers, fishermen, and hikers, with the famous Spirit Lake nestled at the mountain's base. Around 3,000 people lived and worked within the direct impact zone of the mountain, including hundreds of forestry workers and researchers. In March of 1980, 2 months before the disaster, Mount St. Helens began shaking, with hundreds of small earthquakes every day. On March 27th, the mountain emitted smoke and ash for the first time in 123 years of silence, immediately alarming the scientific community. The United States Geological Survey, USGS, immediately deployed an emergency monitoring network of seismometers, tiltmeters, and GPS instruments surrounding the mountain. The most alarming sign was not the smoke or ash, but the north flank of the mountain bulging outward at 1.5 meters per day. This meant a massive magma body was rising inside the mountain and pushing the north face outward like a gigantic blister. By early May, the bulge had grown 150 meters beyond its normal profile, and scientists knew this was a bomb waiting for its trigger. Washington state authorities had evacuated most of the danger zone, but the exclusion boundary allowed some people to remain due to pressure from landowners and the tourism industry. The morning of May 18, 1980, the sky was clear blue, temperatures were cool, and everything appeared as calm as any other spring morning. At 8:32, a magnitude 5.1 earthquake struck directly beneath the north flank bulge. Gravity did the rest. The north flank collapsed completely in under 15 seconds, pulling the highest summit peak down with it. The moment the rock mass slid away, internal pressure was released instantly, like opening a vigorously shaken carbonated bottle. This sideways explosion, called a lateral blast, launched a cloud of superheated gas and ash at speeds reaching 480 kilometers per hour. To put that speed in perspective, it is faster than a commercial fighter aircraft at low altitude, and it reached that velocity within seconds. The temperature of that cloud reached 300 degrees Celsius, sufficient to instantly incinerate and kill every living thing in its path. In under 3 minutes, the lateral blast had flattened all forests across 570 square kilometers, an area equivalent to the city of Chicago. Simultaneously with the lateral blast, the main volcanic eruption began shooting directly upward, creating a massive ash column. That ash column rose at 70 kilometers per hour, and over the next 9 hours, it reached 24 kilometers altitude, piercing through the troposphere into the stratosphere. Compare this to commercial airplanes typically flying at 10 kilometers altitude. This ash column was nearly 2.5 times that height. While the ash column shot skyward, a third danger was forming on the slopes The pyroclastic flows. A pyroclastic flow is not the slow lava you see in Hawaii. It is a mixture of superheated gas, ash, and rock fragments moving at 80 to 180 kilometers per hour. Internal temperatures within a pyroclastic flow can reach 700 degrees Celsius, far exceeding the temperature needed to melt aluminum. This is why no one can survive being engulfed by a pyroclastic flow, not because of burial, but because the surrounding air instantly becomes a furnace. Simultaneously with all of this, the immense heat from the volcano began instantly melting the snow and ice covering the mountain's summit. The meltwater mixed with volcanic ash and debris to form lahars, volcanic mud flows, rushing down river channels with terrifying speed and destructive power. The lahar on the Lateral River moved at over 30 kilometers per hour, faster than the running pace of the world's fastest marathon runner. While lahars devastated the lowlands, volcanic ash from the high eruption column began falling like black rain across surrounding states. In total, the volcano ejected approximately 540 million tons of ash, blanketing 11 states and reaching as far as Canada. In Spokane, 400 kilometers away, ash was so dense that daytime was as dark as night for 4 continuous hours. But among everything that happened that day, the most scientifically remarkable phenomenon was the speed and direction of the initial lateral blast. The energy released by the lateral blast was equivalent to 1,670 Hiroshima atomic bombs, but directed horizontally rather than upward. All of that energy was not directed into the atmosphere, but channeled horizontally along the ground surface, which is why the destruction zone has its characteristic fan shape. While most volcanoes erupt upward, St. Helens in 1980 taught scientists that volcanoes can also erupt horizontally with equal destructive force. For 9 hours after the initial blast, the volcano continued erupting ash continuously, while pyroclastic flows kept cascading down surrounding valleys. By the end of May 18th, Mount St. Helens had lost nearly 400 meters of its height, dropping from 2,950 meters to 2,550 meters. The lost material, equivalent to 3.3 cubic kilometers of rock, earth, and snow, was enough to fill more than 2 million Olympic swimming pools. 57 people died in that day's disaster, including geologist David Johnston, who transmitted his final signal just 2 seconds before the lateral blast obliterated his observation post. Many who died did so not from lack of warning, but because they chose to remain, believing the volcano could not reach where they stood. This was St. Helens's most painful lesson, that the distance that seems safe to the naked eye can be completely insufficient against the force of a lateral blast. In the following days, more than 7,000 rescue workers, cleanup crews, and disaster response specialists poured into the region from across the United States. The Lateral and Columbia rivers were so clogged with mud and drifting logs that boat traffic became impossible, triggering a severe maritime transportation crisis. To clear the Columbia River, the United States federal government had to spend $1 billion just on dredging and channel clearance in the first year alone. Pacific Northwest agriculture suffered severe losses as volcanic ash buried crops ready for harvest across hundreds of thousands of hectares. The timber industry suffered estimated losses of $700 million, with approximately 4 billion board feet of commercial timber destroyed or swept away in the blast zone. Total direct economic damage from the disaster was estimated at approximately $1,100 million in 1980 values, equivalent to approximately $4 billion in today's purchasing power. But the consequences extended far beyond damage. Figures, land, terrain, and ecosystems were fundamentally transformed in ways scientists had not anticipated. Spirit Lake, formerly a crystal-clear, 60-meter-deep lake, was partially filled, and its water level rose 60 meters higher than before the eruption. The terrain transformation along the Lateral River created problems lasting decades as mud and sediment continued washing down into the Columbia River with every heavy rain. But something unexpected happened within the devastation zone that no one had predicted. Nature began recovering far faster than science had calculated. In the grey ash field, with no signs of life, the first flowers appeared just months after the disaster, growing up through cracks in the ash layer from heated soil below. Scientists discovered that pioneer species like dwarf, willow, and algae had survived even under the snow present on eruption day, protected from the blast's heat by the insulating snow layer. Those snow-protected survivors became the nucleus for regeneration, and within 10 years, much of the blast zone had returned to vegetation cover. More than 40 years later, the blast zone has become the world's largest outdoor ecological laboratory, where more than 300 plant species and hundreds of animal species have returned. This is what Mount St. Helens taught ecology, that even after total devastating destruction, life finds its way back through pathways no one anticipated. But the greatest lesson from St. Helens came not from nature, but from the failure and subsequent advance of early warning science. Before 1980, volcanology lacked the tools to accurately predict the precise timing and direction of a volcanic eruption. Following St. Helens, the USGS established the Cascades Volcano Observatory in 1982, specifically designed to continuously monitor all hazardous volcanoes in the Pacific Northwest. Today's modern monitoring system includes dozens of GPS sensors, tracking ground deformation, digital seismometers, infrared cameras, and ultra-sensitive tiltmeters. The lesson from the North Flank bulge taught scientists that ground deformation, rather than seismic activity alone, is often the most accurate warning indicator of an imminent eruption. When Mount St. Helens reactivated in 2004, scientists detected the new bulge and had sufficient time and tools to safely monitor and evacuate the area. That time, no one died, and that is the greatest legacy of the 57 people who lost their lives in 1980. Today, the global volcanic monitoring networks of the USGS and geological surveys of numerous countries are built upon the lessons learned from St. Helens in 1980. St. Helens also transformed how exclusion zones are established and how risk is communicated between authorities and the public during volcanic disaster situations. One of the most critical changes was the recognition that lateral blasts can occur at any steep-sided stratovolcano with sufficient magma pressure. Mount Rainier, just 90 kilometers from Seattle, is ranked among the world's most dangerous volcanoes, in part because of the lessons learned from St. Helens. More than 150,000 people live within Mount Rainier's potential lahar zone, and their evacuation plans are built directly on lahar models observed from St. Helens. One of the most remarkable aspects of St. Helens' recovery is the new lake that formed inside the volcanic crater after the eruption. This lake, called the St. Helens Crater Lake, formed as groundwater and rainwater accumulated in the crater basin and began growing in the early 2000s. The recovery of the St. Helens region demonstrated what ecologists call ecological convergence, proving that nature has multiple pathways to reach a new stable state, even beginning from total disaster. However, full recovery of the old-growth forest ecosystem as it existed before 1980 will take an estimated 100 to 200 years, according to ecologists. This is a time frame no technology can significantly compress, because the recovery of old-growth forest is a biological process requiring multiple tree generations. Mount St. Helens today is one of the most scientifically active research sites on Earth, with dozens of simultaneous research projects ongoing within the zone. Approximately 1 million visitors come annually to the Mount St. Helens National Volcanic Monument, where history and science merge in a landscape found nowhere else on Earth. But beyond all tourism statistics, research figures, or economic damage numbers. What Street Helens truly changed was our fundamental perception of nature itself. Before 1980, many people viewed volcanoes as phenomena occurring in distant places, in other locations, not in the backyard of modern American cities. Street Helens shattered that illusion completely and permanently, proving that geological forces do not respect administrative boundaries or the distances humans consider safe. Today, every time we witness a volcanic eruption successfully predicted in advance, every time a community evacuates in time and no one dies, part of that achievement belongs to Street Helens in 1980. In today's world, with over 800 million people living within 100 kilometers of active volcanoes, this lesson has never been more critical. And among those volcanoes, many have the potential to generate lateral blasts, similar to Street Helens, but surrounded by populations tens of times larger. This is why organizations like the USGS, Japan Geological Survey, and Indonesia's National Volcanic Observatories invest millions of dollars annually in early warning systems. And the question is not whether a similar disaster will happen again, but when and whether we will be sufficiently prepared. That is the final and most important lesson of Street Helens in 1980. Not to fear, but to prepare. Let us look once more at the morning of May 18th at 8:31, 1 minute before everything began. That mountain, so beautiful people called it the Fujiyama of America, stood silent and still in the morning light, giving no sign it had only 60 seconds left in that form. And then the world changed. The story of Mount Street Helens is the story of Earth's power when it decides to renew itself, asking permission from no one. Geology does not operate on human schedules, and Street Helens reminded us of that in a way impossible to forget. Every beautiful mountain you see while traveling, every magnificent range you photograph, is the result of millions of years of geological forces continuously active beneath the surface, beneath your feet. And that is not something to fear, but something to understand. Because understanding is the only truly effective protective barrier we possess. 45 years after May 18th, 1980, Mount Street Helens is still monitored 24 hours a day, 7 days a week, 365 days a year, and every time a sensor detects a small earthquake beneath the mountain, the system automatically analyzes it and sends alerts to the scientific team within seconds. This is the world that Street Helens helped create, a world where we understand nature better and have more tools to engage with it. But alongside all that technology, the most important thing we learned from Street Helens is humility before the true scale of nature. That no matter how many sensors, computer models, and data we accumulate, Earth still retains the capacity to surprise us in ways that have never happened before. Street Helens taught us not that we can control nature, but that we can understand it well enough to coexist with it more intelligently. And that, ultimately, is what this mountain wants us to carry with us after leaving this video. Not fear of what nature can do to us, but curiosity and understanding of a living, breathing planet that occasionally reminds us it is present. That mountain, though it lost 400 meters of its height, still stands there after 45 years, recovering in its own way, waiting at its own pace. And somewhere beneath it, magma is still moving, pressure is still building, and Earth continues its geological story with or without our participation. On May 18th, 1980, we were reminded that we are not spectators of Earth's history, but inhabitants living within it. And understanding, preparation, and respect for those natural forces is what distinguishes those who will survive to learn from them. That is the true legacy of Mount Street Helens, not the destruction it caused, but the understanding it left for generations that followed. The next time you look up at a mountain, Remember that beneath that peaceful beauty is a geological story still being written, and you are standing on one of its pages.